Every time you send a prompt to a large language model, billions of parameters perform trillions of mathematical operations before the model generates a single token. Despite this complexity, every modern language model, either GPT, Llama, Qwen, Gemma, follows the same pipeline. Understanding this pipeline is one of the most important steps towards understanding how these models actually work. In this video, we are going to walk through the entire process, from the moment you type a prompt to the moment the model produces a response. This is not a deep dive into any single component. Think of it as building a meta map. At a high level, every language model performs these operations. Your text is converted into tokens. These tokens become dense numerical vectors called embeddings. Information about the position of each token is added. The sequence then passes through multiple transformer layers. The model predicts the next token. That token is converted back into text. This entire cycle repeats, one token at a time, until the response is complete. Let's go through each stage. Suppose our prompt is the capital of Nigeria is. To a human being, that's a sentence. To a language model, it's just raw text. And neural networks cannot process text directly. They operate on numbers. So the first thing that happens is tokenization. A tokenizer breaks the input into small units called tokens. Each token gets mapped to a unique integer. A token might be a full word, part of a word, a punctuation mark, or even a space. So the capital of Nigeria might become something like a list of numbers. These numbers carry no meaning on their own. They are just lookup keys into the model's vocabulary. The vocabulary is a fixed table of every token the model knows. At this point, our input consists only of integer IDs. But integers cannot express semantic relationship. Token 464 is not similar to token 466 simply because their numerical values are close. So we need a better representation. That's where embedding comes in. A vector, often called a vector embedding, is a long list of numbers that mathematically represents the meaning, context, or properties of text. An embedding converts each token into one of these vectors. Instead of representing a word with one number, it represents it with hundreds or even thousands of numbers. These vectors capture semantic meaning. Words with similar meanings tend to have similar vectors. Rather than representing language as discrete symbols, the model now represents every token as a point in a high-dimensional vector space. Embeddings capture meaning, but they don't capture order. Consider the dog chased the man and the man chased the dog. Same words, completely different meanings. Without positional information, these two sentences look identical to the model. The same token IDs, the same embedding vectors, just in a different order that the model can't distinguish. Before the sequence enters the transformer, each token's embedding is augmented with a positional encoding, a signal that tells the model where the token sits in the sequence. Once positional information has been added, the sequence enters the transformer. This is the core architecture behind modern large language model and is where most of the computation takes place. The transformer consists of a stack of identical layers. Each layer receives the current representation of every token and computes a new representation by integrating relevant conceptual information from the sequence. These updated representations are passed to the next layer where the same process is repeated. As information flows through the network, each token develops a progressively richer representation of both its own meaning and the context in which it appears. Each transformer layer consists of four main components: self-attention, a feed-forward network, residual connection, and a layer normalization. Self-attention allows each token to determine how much information it should gather from every other token in the sequence. In this way, every token is updated using the context provided by the surrounding tokens. The updated representation are then passed through a feed-forward network, which applies additional non-linear transformation to each token independently. Residual connection and layer normalization help stabilize training and enable transformers to scale to dozens or even hundreds of layers. The key idea is that every transformer layer updates the representation of every token, making it increasingly contextual before passing it to the next layer. After all the transformer layers, each token has a rich context-aware vector representation. The model takes the final vector corresponding to the last token in the sequence and projects into the vector space. This produces a score for every token in the vocabulary. The higher the score, the more likely that token comes next. For our prompt, the token Abuja will receive the highest score, Lagos might receive lower score, most tokens will have a score near 0. Once the token is selected, it is appended to the sequence. The entire pipeline runs again from the top. Tokenization, embedding, positional information, all the transformer layers, prediction, one new token. This process is called autoregressive generation. Each token is conditioned on everything that came before it, including the tokens the model itself has already generated. And the response you see on your screen is the result of the cycle repeating, typically hundreds of times, often in just a few seconds. Let's go back and look at the full picture. A language model converts text into tokens. Tokens become embedding vectors. Positional encoding preserve word order. Transformer layer, which consists of self-attention, feed-forward network, residual connection, and layer normalization, build increasingly rich contextual representation. The model projects the final representation into vocabulary space, producing a probability distribution and picks one token. That token joins the sequence and the whole thing starts again. This pipeline is the foundation of every modern large language model. In the next video, we will go through each component, starting with the tokenizer and work our way through embedding, positional encoding, attention, and eventually the full mathematics of the transformer. Once you understand the components, you understand just now how to use these models for why they work.